Hi everyone, I'm Santhi from Department of Mathematics and Statistics, Bhavan Vivekananda College. I'm here with my lesson 19 from linear algebra on vector spaces. In this lesson, I'm going to explain some results on null space and column space of a matrix and some problems based on these results. Let us prove now a theorem on null space. Prove that the null space of an m by n matrix A is a subspace of Rn. So this is what we checked even in the previous problems. Any vector x, if it has to be in the null space, if x should belong to null A, where A is an m by n matrix, then first condition is x must belong to Rn. Right, that is here number of columns. So the same thing, if we apply the same thing, then here the set of all the vectors in the null space, that is null A, the null space of an m by n matrix A is a subspace of Rn. This is what we have to prove in this theorem. So let us prove the theorem. So we are given let A m by n be a given matrix. So you are given a rectangular matrix A m by n of order m by n, and now let us write what is null space. Null A is equal to set containing vector x. Where will be the vector in the null space? It belongs to Rn. That means it will be with n rows such that it should satisfy the condition Ax is equal to 0. Now when you take vectors from Rn, so in this set null A, all the vectors from Rn which satisfy the equation Ax is equal to 0. So this will be obviously a subset of first Rn. Now what do you have to prove here? Null A is a subspace of Rn. Now we know we have three conditions to prove any set to be a subspace. So the first one, let us take the first one, that is 0 vector. So let us consider 0 belong to Rn. Then 0 belong to Rn, then when will it be there in null A? It should satisfy the equation Ax is equal to 0. So consider Ax is equal to 0, then implies A into 0 is also equal to 0. Therefore, we have the 0 vector belong to Rn such that A into 0 is equal to 0. So it is satisfying these two conditions. X belong to Rn, Ax is equal to 0. Then that X will be null A. That implies 0 belong to null A. The 0 vector, whatever you have taken in Rn, it belongs to null A. Now let us look at the second part. Second condition, what do you have to prove? So the second one, we have to take two vectors. So suppose x1, x2, and then you have to prove x1 plus x2 is also there in null A. This is what we have to prove. So let us try to prove it. So I'll consider x1 comma x2 belong to null A. Belong to null A, and you have to prove that x1 plus x2 belong to null A. This is what you have to prove. So, now x1 comma x2 belong to null A implies, so what are the two conditions they have to satisfy? x1 comma x2 belong to Rn, and Ax1 is equal to 0, Ax2 is also equal to 0. That implies now let us consider, not implies, let us consider now x1 plus x2. Then this belong to Rn because x1 ka x2 belong to Rn. Therefore x1 plus x2 also belong to Rn, and what will be a into x1 plus x2? That is equal to ax1 plus ax2. What is ax1? 0. What is ax2? 0. That implies a into x1 plus x2. If it is equal to 0, then it is equal to 0. Hence, x1 plus x2 belong to null A, because x1 plus x2 belong to Rn, x1 plus x2 belong to Rn, and x1 A into x1 plus x2 is equal to 0. Therefore, the summation will be in null A. So, the second condition is also over. Now, the third condition for the subspace. So, in third condition, what do you have to take? Consider a scalar C and x1 belong to null A. That implies, what about x1? We have x1 belong to Rn and ax1 is equal to 0. Now you have to prove that cx1 belong to null A. We have to prove that cx1 belong to null A. So when will cx1 be in null A? You have to prove two conditions. So that is, now c into x1 belong to Rn. Why? Because since x1 belong to Rn, this is the first one, and the second one, a into cx1 is equal to, now c is a scalar, it's not a vector. I can write it as c into ax1. What is the reason? Since c is a scalar. So this will be equal to c into what is ax1? 0, which is equal to 0. That implies we have a into cx1 is equal to 0. So you have two conditions. First one is cx1 belong to Rn and a into cx1 is equal to 0. Hence, cx1 belong to null A. So you proved three conditions. Now cx1 belong to null A, and before that is x1 plus x2 belong to null A, and the first one is we proved here where is 0 vector. 0 vector belong to null A. So by all these three, by all the above, we have null A is a subspace of Rn. Remember, it is not Rm. A is a matrix with m by n order, m rows, n columns. But here you have to prove it is a subspace of Rn, not Rm. This you have to remember. So this theorem is completed. Now let us prove the second theorem on column space. That is, the column space of an m by n matrix A is a subspace of Rm. So let us try to prove this proof. So what is given here? Let A m by n be a matrix. This is a given matrix to us. And then what is column space of A? By definition, column space of A is having all those vectors B belong to Rn such that Ax is equal to B for x belong to Rn. This is column space. Then obviously this will be a subset of Rm because it has all the vectors from B. So we have column A is a subset of Rm because it has all the vectors B which are there from Rm. Now we have to even prove that this is a subspace. So for subspace, what are the three conditions? We have to prove 0 vector, and sum of two vectors is again a vector in the same set, and product of the scalar multiplication, product of a vector and a scalar is again in the same set. So first one, let me take here. First one, so 0 vector in Rm. So let 0 belong to Rm, then we have 0, let me take it as 0 dash, another vector we have 0 dash in belong to Rn such that A into 0 dash is equal to 0. That is 0 satisfies the equation Ax is equal to 0. Then implies we have this 0 vector belong to column A. 0 in Rm belong to column A. That is the first condition. Now let us take the second one. So let B1 comma B2 belong to column space A. What do we have to prove? To prove that B1 plus B2 belong to column A. So now I have since B1 comma B2 belong to column A. So if there is a B in column A, then there will be X that will be there in Rm, and there will be X related to B. There will be X related to B in Rn such that Ax is equal to B. So now I have B1, B2 belong to column A implies there exists X1, X2 belong to Rn such that Ax1 is equal to B1 and Ax2 is equal to B2. This is equation 1. Now what do I have to prove? That B1 plus B2 belong to column A. So we have to prove that A into B1 plus B2 is equal to X1 plus X2. Sorry. A into, we'll have X1 plus X2 is equal to B1 plus B2. This is what we have to prove now. Now I have X1, X2 in Rn. Then X1 comma X2 belong to Rn implies X1 plus X2 also belong to Rn, and A into X1 plus X2 is equal to Ax1 plus Ax2. Now what is Ax1? B1 plus B2. This is from whatever the equation here you have one. Ax1 plus Ax2 is equal to B1 plus B2, which implies B1 plus B2 belong to Rn. Now let us look at the third condition. That is the let C be a scalar and B belong to column space A. To prove that CB belong to column space A, you have to prove this one. This is to be proved. Now B belong to column A implies there exists X belong to Rn such that Ax is equal to B, where this B will be there in Rm. Right. Now B belong to Rm implies C into B also belong to Rm, and A into X is equal to A into we want CB known, so A into Cx is equal to. So this I will write it as C into Ax, which is equal to C into B. So this, if you observe, implies we have CB belong to Rm such that A into Cx is equal to CB, where Cx belong to Rn. Hence we have CB belong to column space A. By all the above, we can say that column A, column space of A is a subspace of Rm. Hence, this theorem is proved. After completing these two theorems, we will do a problem basing on these two theorems. What is the result of both the theorems? If you take a matrix A m by n, then null A is a subspace of Rn, where n is the number of columns. This is Rn I say, where n is the number of columns. Let me write it clear. So it is Rn. And whereas column A is a subspace of R M, where M is the number of rows. Now let us look at this problem. For the following matrices, find K such that null A is a subspace of Rk. Then B bit, find K such that column A is a subspace of Rk. Now let us look at the first one, A. What is its order? It is a 3 by 2 matrix. So here you have m by n. So I have here first the first question, m is equal to 3 and n is equal to 2. Now what is A bit answer? Find K such that null A is a subspace of Rk. So here for this K should be null A, we have subspace of Rn, where n is so R2. So null A is a subspace of R2 means here you will have K is equal to, so first A bit answer for this is K is equal to 2. Let me write with another color. K is equal to 2. So for A bit, K is equal to 2, where null A is a subspace of R2. I have here R2. Similarly, what is second bit answer for this? B. Second is column space. What do we have here? Column space should be column A should be subspace of R3. So here K such that column A is a subspace of Rk means K is the number of rows. So I should have K is equal to 3, where column A is subspace of R3. This is for first question. Now let us look at the second question. So here, what is this order? It has 4 rows and 3 columns. So my A bit answer will be here. So here this is M and this is N. So what is null A? Null A is a subspace of Rn. So here I should have K is equal to 3 such that null A is a subspace of R3. Now what is the B bit answer here? K must be equal to number of rows such that column A is a subspace of R4. Now let us come quickly here. This is a matrix with the 2 rows and 1, 2, 3, 4, 5 columns. So I have for A bit answer is K is equal to 5. Null A is a subspace of R5, and B bit answer is K is equal to 2 number of rows such that column A is a subspace of R2. Now let us come for this question. So here A bit, this is a matrix with one row and 5 columns. So here for K, for null A, what is the, now it should be equal to number of columns, where I have this null A is a subspace of R5, and similarly here K must be equal to 1, where column A is a subspace of R. How many rows? Only one you have. So it is only one element will be there. Column A is a subspace of R1. This is what. Now we'll look at the next problem. So here it is asked, find a matrix A such that the following set W is equal to column A, where W is given as set containing B minus C to B plus 3D, B plus 3C minus 3D, C plus D such that B, C, D belong to R. Now let us look at the solution. So what is W given as? It is decided by three parameters you can observe. B minus C to B plus 3D, B plus 3C minus 3D, C plus D. So I can write it as a linear combination of three vectors because there are three parameters. B into 1 2 1 0 plus C into minus 1 0 3 1 plus D into 0 3 minus 3 1. So by this what can we write? W is equal to span of three vectors. So it is a span of three vectors and it is given this W is equal to column A. So this span of three vectors is equal to column A. What does it mean? This column A is a linear combination of three vectors. Then what is our definition of column A? If A is a matrix, then column A is nothing but linear span of the vectors columns in the matrix A. So what can we have? A as A will have these three as columns, so that its column A will be span of this set. So we have column A is equal to set of all linear combinations of columns of A. Therefore, if I take A as a matrix with these three columns, first column is first vector here, second column is second vector, third column is third vector, then this W will be equal to column A. Let us look at this practice problem. Find a matrix A for which the set W is equal to the same way. It is 6A minus B, A plus B minus 7A such that A comma B belong to R is column A. So in the same way you can work out this problem.